Let me first thank the organizers for this opportunity. My name is Jed, and together with Tommaso, we'll tell you about a practical relativistic bit commitment protocol. And this is based on joint work with Felix, Rafael, Marco, Stephanie, and Hugo. Okay, very brief outline of the talk. First, I'll tell you what a commitment scheme is. Then I'll tell you why relativity is useful for these kind of schemes. And then I'll give a brief overview of what was known before we kind of started working on this. So this is called the relativistic bit commitment field. And then I'll be more specific, and we'll discuss the two-round protocol by Simard, which now we can prove security against the most general quantum attack. But it only gives you security for a finite time, limited time. And then we propose a new multi-round protocol, which we can only prove security against classical adversaries, but the commitment time can be arbitrarily long. So somehow there's this trade-off. And then Tommaso will tell you how to implement both of these schemes in practice. Okay, what is commitment schemes? Well, it's a way to commit to a certain string without revealing it. So usually you have two phases. Say Alice has a piece of some information, and you should think of it as a kind of a safe. She wants to put it in a safe, send the safe to Bob, and this is the commit phase. Now it's over, and then at some point later she will send the key to Bob so he can actually open the safe and read the message. Okay, and what are the security guarantees that we're after? Or in other words, what are the cheating objectives of the dishonest parties? So if Bob is dishonest, he just wants to break the safe and read the message without kind of waiting for the key. If Alice is dishonest, then she wants to influence what's kind of written inside the safe. So you can kind of think that maybe she's got two different keys that she will try to send to Bob in the open phase, and they kind of reveal different messages. I mean, if she can do that, then the protocol is broken. Okay, to be more specific, suppose that Alice is honest. So these are more formal kind of statements. If Alice is honest and Bob is dishonest, then Alice has a bit that she wants to commit to, and she will act honestly. Bob can do anything, but what we want is that whatever he does, he cannot guess what this bit is. So more formally, the transcripts corresponding to different bits should be indistinguishable. Then if Alice is dishonest, then her cheating strategy will consist of kind of two parts. There's going to be some kind of generic commit strategy, and then for the open phase, there will be two different open strategies depending on what she actually wants to unveil. Okay, so somehow there is this generic commit and then two different open strategies. And if she can do that, if she can open both bits with reasonably high probabilities, then again, the protocol is broken. So you can kind of see this security for honest Bob as a game in which Alice performs some generic commit. And then in the open phase, she's challenged to open one of the bits with equal probabilities. And then she wins the game if Bob accepts the commitment. And it's clear that she can win this game with probability 1/2 just by doing an honest commitment to one of the bits. So essentially what you want is that whatever she does, whatever dishonest strategy she applies, this 1/2 is, maybe she can improve it by an epsilon. So we want that the winning probability is maybe 1/2 plus epsilon, where this epsilon should be exponentially small in, I don't know, the number of bits exchanged or some kind of security parameter. And note that this is equivalent to the usual definition where you take probability of successfully opening 1 plus probability of successfully opening 0 is less than 1 plus something small. Okay, now relativity. Why is relativity interesting for the purpose of commitment schemes? Well, suppose that this is a space-time diagram, then you have two events, the red event and the blue event. And if this is the arrangement, then there's no communication between the two events. They are space-like separated. So whatever happens at these two, so it's easy to convince yourself that this is essentially a model with two isolated provers. And this is kind of nice because these models have been well studied in computer science, and we know exactly what kind of operations you can execute in this model. So this is what I'm going to call a two-round protocol. You have the commit round in the red dot, and you have the open round in the blue dot, and it's essentially a two isolated provers model. Now, if we add more events, for example, now you have this green event, then you realize that, okay, there are some communication constraints, but for example, clearly you can have communication from red to green. So it's not quite a three isolated provers model, but it's something in between. So I just want to argue that more complicated relativistic scenarios cannot be cast as simple non-communication models. So somehow this is a richer world and more difficult to describe. Okay, so this is just an outline of what people have done in this field, and I guess the first protocol was proposed by Ben Orr in 1988, and this is just a two-round protocol, so you have the commit phase and you have the open phase, and they proved security against classical adversaries. And obviously, this is done in the kind of two-prover language, because this is the computer science approach. And then Kent proposed two multi-round protocols, which, well, I guess, yeah, so they explore the relativistic side of things. So you have these relativistic constraints. The only issue with these protocols is it's kind of difficult to extract explicit security bounds from these papers. And then in 2007, Simard simplified the protocol by Ben-Or, and he proved security against a restricted class of quantum attacks. And then recently there were some more quantum protocols, because note that the first, all the protocols I described before are actually inherently classical. So even if people prove quantum security, it's just against quantum adversaries. You don't actually need any quantum to execute the honest protocol. Okay, so what did we want? Why did we start this project? We wanted to achieve a commitment time of more than 40 milliseconds. 40 milliseconds is what you can do if you just have 2 rounds. And this is limited by kind of the size of the planet. So if you commit on one side of the planet and then you open on the other one, you can achieve about 40 milliseconds. If you want to go longer, you have to have more rounds. And so we wanted to have a multi-round protocol which is kind of simple, can be implemented using currently available technology, and for which we can have a rigorous security proof. And so we started by looking at Simard's protocol. We realized that security against quantum adversaries for this one corresponds to a certain non-local game which has been solved recently. So now we have a we have a security proof against the most general quantum attack. And then we also propose a new multi-round protocol for which we can prove security, but as for now, only against classical adversaries. And we've also implemented both of these schemes. Okay. So what is this 2-round protocol that I mentioned? As I said, for 2 rounds, we're essentially in a 2 isolated provers model. So A and B are private strings of Alice and Bob. In the commit phase, Bob sends a random string to Alice. She takes a bitwise AND with the bit she wants to commit to. This is D. And then she also XORs it with a fresh random string. And this is just to protect herself. And she returns that to Bob. In the open phase, she will just say, look, I committed to 0, and this is the randomness I used to mask my string in the previous round. And security for honest Alice essentially is guaranteed by the XOR property. I mean, if everything that Bob receives in the commit phase, there's just one string, and if you receive something that has been XORed with fresh randomness, it contains no information about it whatsoever. Security for honest Bob is more complicated. And let me just now go to the game picture. Okay, in the game picture, there are 2 Alices. There's the commit Alice and there's the open Alice. One of them receives a random n-bit string. This is the string from Bob. The other one receives the kind of the challenge. This is what she's supposed to open. So now you can think that maybe there is some kind of referee that tests how well she's able to cheat. They have to output something, and they have to satisfy this condition. So this is essentially a non-local game. You can convince yourself easily that classically you can win this with probability 1/2 plus 2 to the minus n. And recently it has been proven that quantumly the winning probability is bounded by 1/2 plus something that behaves like square root of 2 to the minus n. Okay? So you have exponential decay even against quantum adversaries, and it's conjectured to be essentially tight. And you have this interesting feature that it's a fully classical protocol, but you have this kind of quantum classical gap. So it seems like the quantum adversary is strictly more powerful, which I think is quite interesting since the protocol is fully classical. Okay, so this is a 2-round protocol, and now we want to go longer. We want to extend it. We want to have more rounds. So now we're back to the relativistic model. So you remember that this is not a fully kind of isolated provers model. Now we just have these kind of causal constraints. And actually, the only constraint that we require is that every pair of consecutive rounds is space-like separated. So there is no communication between consecutive rounds. Okay? The commit phase is exactly the same. And previously, in the second round, Alice would just unveil A1. Okay? Now what we want her to do is she receives a random string from Bob. She combines her fresh randomness from the first round with this random string, and she does it using a finite field multiplication. We found that this is the structure that's useful for this task. And again, she has to mask it with a random string. This is A2. And they keep doing that. And then in the open phase, again, the open phase is very similar to what we had before. She unveils the bit and somehow the last random string she used. Okay, and security for honest Alice is again guaranteed by the XOR. Everything that Bob receives before the open phase has been XORed with a random string, so this is all kind of fully uniform. No information about the commitment. Now, security for honest Bob becomes actually quite complicated because if you think about it in the game picture, okay, the first Alice, she receives B1, she outputs something. The second Alice, she receives B2, but she also receives the challenge, okay? This is the bit that she's challenged to open. And it's actually very important that she receives it already. And if you want to know why, you can ask me afterwards, but this bit D has to appear in the second round already, and it will appear until the very end. They keep doing that, and then the last Alice doesn't receive anything from Bob. She still receives the bit that she's trying to unveil. And then there's the verification function, and then obviously this is quite a difficult game to analyze, because at least from the quantum mechanics point of view, there are all these causal constraints that tell you which parties cannot communicate, but then all the other parties can communicate. So there could be plenty of communication and even quantum communication going on. So it seems like analyzing this is very hard. I think even for 3 rounds would be very difficult. Classically, you can simplify this, because we know that shared randomness doesn't help. So you can just think of deterministic strategies. And so then you can just think, okay, every output is just a deterministic function of all the inputs that are kind of available at this point of space-time. So you can think that this kind of flattens the structure of the protocol, and you just get a kind of a multi-prover game, or like a multiplayer game. So in here we have like n+1 kind of rounds, and it collapses to this game where you have n+1 players, and they all kind of receive inputs and answer in parallel. And so note that some of the inputs they receive come from the round that they kind of belong to in the previous slide, whereas some other inputs kind of come from the past. You can think that their kind of colleagues from the past transmitted it to them. The important thing is that every party is missing at least one of the inputs, and this is kind of crucial for security. And so, okay, they output something, they check this, and the nice thing is that this transformation, so this relation between the cheating in the bit commitment protocol and this multiplayer game is actually exact. So if you manage to calculate the optimal winning probability, it will be the same. Okay, the conclusion. So cheating in this quantum bit commitment collapses to a complicated n+1 player game with no communication. And the exact cheating probability is difficult to calculate. You can relax the problem to the problem of computing a certain function in the number on the forehead model. This is a well-studied model in computer science, and these kind of problems are believed to be hard, which would imply that the cheating is difficult. But unfortunately, people don't know how to prove it. And this is actually a class of big open problems in computer science. Or equivalently, you can see it as counting the number of zeros of a certain family of polynomials if you're algebraically inclined. So in the end, what we can prove is that we can have security for honest Bob, which is exponential in n, but unfortunately it scales quite badly with m, which is the number of rounds. So essentially, every time you add a round, you lose half of your decay exponent. And this looks quite bad, but unfortunately, this functional dependence, n divided by 2 to the m, looks very similar to what people have been getting in communication complexity. So maybe there is a kind of a deeper reason why we hit that bound. So in principle, we can have arbitrary long commitment at the price of very large n. Unfortunately, in practice, n is limited by our bandwidth and how quickly we can exchange information. And since we rely on timing constraints for this relativistic assumption to hold, well, we can actually, the technology limits our commitment time. And I guess now I hand over to Tommaso.
In this panel left, I want to show you how can we implement this protocol, and I want to convince you that this kind of protocol is kind of very easy if you rephrase in a very simple way. So the crucial point is that we have two separate, our experiment, our laboratory is shared between two separate locations. Location L, in L, and 0, okay? And we have that Alice and Bob, they share a reference, a time reference, and a position reference. So they agree where the protocol is happening. And also they agree also on the time when the protocol starts, we see before, and also Alice share with her friends in the other location some random bits that she needs to perform the protocol. So the commitment starts with Bob. Just said that with Bob, they challenge Alice to commit a bit. And he challenged Alice using a string of n bits. Then Alice encodes the commitment bit using this formula Bob did show you before. So if she wants to commit to 0, she just answers A. If you want to commit to 1, she answers the XOR between the two. And that's guarantee the concealing constraints. Now you can imagine that when B left Bob, then you can imagine to draw this line, which represents the speed-like communication. Everything that is happening here cannot be influenced by what is happening here. On the contrary, what is happening here can be influenced by this node. Okay, so the commitment end and is opened by simply when Alice announces the string A and the commitment B, D. And now it's important that to guarantee the time constraint so that the time T2 is smaller than T1 plus over L over C, and that's just the relativistic constraint. Now we know that this kind of protocol, as Jed showed, is limited, the commitment time is limited between the distance between the two guys. So if you want to go for multi-round, what you do, you simply perform, okay, the first round is exactly the same as before, and during the sustain round, Bob challenged Alice to sustain the commitment using a string B2, and Alice answered this rather complicated formula, which is a multiplication between two strings of large number, possibly a large number, and then XOR. And you can continue to perform this protocol, and every time that you sustain the commitment, you gain some commitment time. And when you want to open, you just unveil the last string A2. So we just show that the security of this kind of protocol is, we can show that the two-round protocol is probably secure against quantum and classical adversary, and the multi-round we show security against only classical adversary. And the formula of the security parameter are written here. So in the first case, it's nice because the security parameter scales with the number of bits. So even few bits allows us to give a very high security. On the contrary, for the multi-round scheme, the security parameter scales with the number of bits in a good way, if you want, and with the number of rounds in a bad way. This recursive formula is similar to the one that Jed presented before, or is approximated. So if you just plot this formula and you put here in log scale the security parameter, you see that even using a large number of bits, you can guarantee security up to, let's say, 10 to the minus 5 only for few rounds. Okay, that's the number where we play. So we play with the 512 bits, and we perform 6 rounds. Okay. So now, if you want to play your game with the 500 rounds, you need powerful resources that allows you to perform this multiplication in a fast way. So the key point is to use, I don't know, two FPGA in our case to perform the round. The round consists, I remember you, in a multiplication and transfer of information. And to transfer the information, we use this optical link. Then in our case, we perform one round in 6 microseconds. This limits the minimal distance you can play. And also, you need a clock, a reference clock for the two guys. In our case, of course, to guarantee security, you need one clock for each guy, and in theory, you cannot use a GPS as in our case. You can use, I don't know, atomic clock or something like this. But it's feasible to guarantee a shared asynchronized clock for the two Alice and Bob. So we did this experiment between Geneva and Bern, and you can probably hardly you can see is 130 kilometer distance the two locations, and that's guarantee 437 microseconds of commitment time. So that's probably the most easy way that I can show you to convince you that the experiment is relatively easy, because you see the tabletop of this experiment is just a couple of PC and FPGA, but you have to rephrase your experiment in a nice way, because otherwise it can be harder. So you have to guarantee that the clocks are synchronized. We verified the synchronization between the GPS clock in Geneva and the datasheet of the clock that tell you that the uncertainty is on 150 nanoseconds. So it's much, much smaller than the commitment time that we are going to perform. So you calculate the commitment time. You have, 437 microseconds, which is the distance between Bern and Geneva. You subtract the time that you require to perform your round, the uncertainty on the clock, a buffer time that considers some imperfection. At the end, you arrive 400 microseconds of commitment time. You multiply for the number of rounds minus 1, because 1 is the opening, and that's give you a commitment time, in our case, between Geneva and Bern of 2 milliseconds. Okay, this is not, of course, this is not smaller. This is smaller than the 40 microseconds that Jed was telling before, But now we can think at the experiment we performed last year, and we already showed that we can perform an experiment between a synchronized experiment between a very far distance, very far location. In our case, what we did last year was 9,300 kilometers, and the commitment time in that case was 60 milliseconds because we use a quantum relativistic big commitment. So now we plug our number, and we see that already in the 2-round protocol, the classical relativistic big commitment has a gain compared to the previous one, and actually in the 6-round protocol, we can arrive to something which is not achievable with a 2-round protocol on the Earth. That's the game. And that's probably one of the next step. So with this, I arrive at the end of the presentation. So we have shown that relativistic classical big commitment can be proven against quantum and classical adversary, can be proven secure. We have shown that in theory, I mean, at least for against a classical adversary, we are not limited in time. We can perform a relativistic big commitment and use a multi-round scheme, and so achieve this commitment time longer than just the distance between the two laboratories. And finally, we show that the experiment is quite easy to implement. It's requires only a synchronized clock and some powerful resources to perform our classical operation. And with this experiment, we can easily achieve commitment time longer than one we can achieve with a single round protocol on the Earth. So with this, I conclude. I want to thank the University of Bern for giving space to perform the experiment, funding QCrypt and the Ministry of Education and National Research in Singapore. And also, I want to advertise the Single Photon Workshop 2015 it will be in Geneva, and so remember the date, probably soon in the website where you can find information. And also, I will remember that there is 2 posters that are presenting practical QKD over 300 kilometers and countermeasure against blinding attack, and the talk of Jed on Wednesday, so tomorrow. With this, I finish.
Achieve a result superior to communicating straight through the Earth, but that requires neutrinos, I think. So if you decide to discount attacks that involve neutrinos, and you have to go around circumferentially, do you still do better than the straightforward method?
You apply the same security with the multi-round, and then you can do better with the multi-round again.
Good.
Then you gain anyway.
So if I understand correctly, you need your Alice to be in 2 places, right? Both in Geneva and in Singapore. So do you assume to prove security for Bob that he accepts that Alice is really in Geneva and in Singapore, or can he test? What if Alice is closer by and your light cone, actually she's inside the light cone instead of outside? Or
We actually need that also Bob is into place, and this guarantees the position of Alice's. I mean, Bob is looking at that. In our case, they are in the same room, okay, but if you want to, I mean, you can
somewhere and Alice is somewhere, it can be all around the circle around Bob, right?
Yeah, but this is this uncertainty you can consider in your buffer time, and it's much smaller than the distance between the 2 positions. You can also synchronize the answer. I mean, in our case, we synchronize the answer, and also if the communication between Alice and Bob takes too much time, she can pass the relativistic constraint. So you have to guarantee anyway that the answer arrives in time.
Both players to be at the same, basically very close to each other in 2 different locations.
Yeah, but
okay.
Actually, I have one very short question. What stops you just doing this protocol many times and just expanding the number of rounds?
So I was here. When you do multi-round, we decided to fix the security. We choose the security parameter the same as we demonstrated before. And you see that with this multi-round scheme, since we cannot, maybe I just say what you were saying also before, it's not easy to guarantee that, to quantify how many information leaked out in all the direction, because you have only the last two rounds are the two last round are satisfy the relativistic constraints. All the information before can leak in all the direction, and that's much the protocol more difficult to be demonstrated. But I don't know if you want to add something, Jeff.